A very good morning to all the students. I am Dr. Hima Bindu from the Department of Mechanical Engineering, and I'll be dealing the subject robotics in Institute of Aeronautical Engineering. And in today's session, we'll discuss about few problems solving in various conditions. Right. So firstly, let me read the question. Determine the time required for each joint of a 3-axis RRR manipulator to travel the following distance using slow motion. Joint 1, 1000, joint 2, 300 and joint 3, 600. All joints travel at a rotational velocity of 150 degrees per second. Now what do we need to calculate? We need to determine the time. Right, we need to determine the time for the 3-axis manipulator, where each and every joint is having different sort of distances like 1000, 300 and 600 for joint 1, joint 2 and joint 3, and the rotational velocity is being considered as 150 degrees per second. So here we have written the data, right? The rotational velocity is 150 degrees per second. The joint 1 will be traveling at 1000 degrees, joint 2 will be traveling at 300 degrees and joint 3 is traveling at 600 degrees. Right? Now let's calculate the time for each joint. We need to calculate it is being told to calculate the time for each joint. Right? So we need to calculate the joint at the time for each joint. So coming to the joint 1 and time 1, we are taking it as time is equal to the joint angle by the velocity, rotational velocity, right? That is nothing but 1000 by 150 for T1, right? Whereas for T2 it is equal to 300 by 150. 43 is equal to 600 by 150. In this form, we will be calculating the time at each joint, and the time for joint 1 is being taken as 6.67 seconds, right? And the time for joint 2 is considered as 2 seconds, and time at the joint 3 is being considered as 4 seconds when we are calculating. Right? So at joint 1, 6.6 seconds, joint 2, 2 seconds, and joint 3 it is 4 seconds. Next, moving on to the next problem. Explain the trajectory planning and show how the trajectory planning is done in case of point-to-point robot having constant maximum velocity and finite acceleration and declaration, right? So we need to find out the trajectory planning and show how the trajectory planning is being done to PTP robot, right? So initially the solution will be considered as, initially the trajectory planning in robot involves the determination of the path that the robot's end effector or the robot should follow. Right? Trajectory planning is nothing but it involves the path that the robot's end effector or the joints should follow over a period of time, right? Over a certain period of time to move from a starting position to a desired end position, right? To move from one initial position to the desired end position. Right? So this particular strategy includes specifying the position. We need to specify the position, the velocity and the acceleration with respect to the time. Right? Here the proper trajectory planning is crucial to ensure that the robot moves smoothly, effectively and within its physical limits. Right? That is known as the trajectory planning. Now let us see how the P2P trajectory will be done. So what do we mean by point-to-point trajectory planning? That is, we need to have a proper planning within the robot where the point-to-point axis is being given to the robot. That is, the robot is required to move from one position to another. Right? The robot is required to move from one position to the another without specific concern for the path taken between these points. Right? Without any sort of specific concern from the path between these particular point to from one point to the other without any specific consideration. So the goal is to move from the start to the end position as quickly as possible, or as effectively as possible. When the robot is moving from one initial point to the other end point, right? The goal should move it should move very quickly and more effectively, efficiently, right? As quickly as possible. So when we are considering this particular point-to-point trajectory, the constant maximum velocity Vmax, we should consider the constant maximum velocity, and we need to also consider the finite acceleration and deceleration, right? Other than the finite acceleration and deceleration, with respect to the maximum velocity, right, we need to find out the point-to-point trajectory planning. Now here, as we have told, the robot should move from one position to the other with a specified constraint within one particular path. Now we need to find out the acceleration phase, we need to find out the constant velocity phase, and we need to find out the deceleration phase. Right? So what do we mean by acceleration phase? Then the robot acceleration from rest to the maximum velocity. Right? When there is the robot acceleration from rest to the maximum velocity, that is known as the acceleration phase. Or when the robot moves at the maximum velocity, then that is known as constant velocity phase. Or when the robot is deceleration to the rest, then that is known as deceleration phase. Right? So the first step which is involving the P2P trajectory planning is acceleration phase, where we are considering the time, that is Tmax, as velocity, maximum velocity by the acceleration, right? Where time is being considered as maximum velocity by acceleration, or the distance is being considered as t is a half at1 square, right? Where a is nothing but the acceleration, t is what we have calculated here, that is the time, right, and a is the acceleration. So we will be getting d, or we can also write it as 1 by 2 v square max by a. That is, we are inserting t here, right? We are inserting t here, right? So this is how we calculate the distance and we calculate the time with respect to the acceleration phase. That is, during this particular phase, the acceleration from 0 to maximum velocity with a constant acceleration a will be calculated as these particular two formulas. Let us consider a few cases for the different trajectory phases. That is, when we have acceleration, constant velocity, and when we have deceleration. How do we write these particular three phases? Or when we have just acceleration and deceleration, how do we write down this particular phase? That is, no constant, when we are not considering any sort of velocity. How do we write the equation? That is, when we are considering all these constraints like acceleration, constant velocity, and deceleration, we need to ensure that t should be greater than d1 plus d3. Right? We need to ensure that distance d will always be greater than d1 plus d2 or d1 plus d3, so that there is no non-zero t, so that we will not have any non-zero t, that is, it will not be equal to 0. And when we are considering only acceleration and deceleration without the velocity, the total distance is small. D will be smaller than Vmax. Right? D is smaller to the robot might accelerate to Vmax and then immediately deceleration without maintaining a constant velocity. In this case, the time and the distance equation adjust and we can solve the quadratic equation. right? When we are considering d is smaller than v max, then the distance equation adjusted can be solved by using the quadrant equation. This is the sample calculation, how we can do this particular sort of problem when we have acceleration and deceleration, right? When we need to calculate T1 and D1 for acceleration and T3 and D3 for deceleration, right? We need to calculate T1 and D1 for acceleration, and we need to calculate T3 and D3 for deceleration. Now, this is the equation which we have. We need to determine, that is, D should be greater than D1 plus D3, right? The overall distance should be equal to distance of point 1 plus distance of point 2, right? Distance of point 1 plus distance of point 3, sorry, right? So if we are calculating this T2 and D2, there will be no adjustment calculation to have any acceleration and deceleration. Now, when we are calculating D1 and D3, we also should know what is the time to for point 2 or what is the distance at what it is traveling, right? So when we are considering that, there will be no adjustments with respect to the acceleration and the deceleration, right? So this is how we will be doing the sample calculation when we have acceleration and deceleration in the trajectory planning, right? Next, moving on to the third problem. A single link rotary robot is required to move from theta 0, which is equal to 45 degrees, to theta 2, that is from initial position to the final position. It is moving at an angle of 45 degrees and 90 degrees. In what is the time? In 2 seconds, right? So the joint velocity and acceleration are 0, right? The joint velocity as well as the acceleration are 0 at initial and the final position. The joint velocity as well as acceleration is equal to 0 in the initial position is at point 0 and the point 2, right? In the initial position and the final position. What is the highest degree polynomial that can be used to accomplish the motion? That we need to find out. Already we have initial position, it is at an angle 45 degrees, right? And at the final position, it is at an angle of 90 degrees. Right, at the initial and the final joint velocities are 0, that is theta dot is equal to 0 and theta dot 2 is also equal to 0, and the acceleration is also equal to 0, that is theta. Velocity we are writing it as theta dot and acceleration we are writing it as theta dot dot. So both are also equal to 0 at the initial and the final position. So what is the equation for to calculate the polynomial degree? So equation to calculate the polynomial degree is that theta with respect to time is equal to a naught plus a1t plus a2t square plus a3t cube plus so on up to a naught tn, right? With this particular equation, we will be calculating the what we have asked us to calculate. What is the highest degree polynomial? We will be calculating the highest degree polynomial. This is already given. Theta dot, that is velocity with respect to initial point is 0, velocity at final point is 0, acceleration at initial point 0 and acceleration at final point is 0, and theta at initial point is 45, theta at final point is 90 degrees. This is 0, right? It is 90 degrees. So to satisfy all these particular 6 boundary conditions, the polynomial must have at least 6 coefficients, right? In order to satisfy all these particular conditions, the polynomial should have at least 6 coefficients. So the highest degree polynomial needed is a 5th degree polynomial. So the highest degree required is the 6th degree polynomial. Thus, the highest degree polynomial that can be used to accomplish the motion is the 5th degree, right? With the help of this particular equation, we have come to a conclusion that in order to find out the highest degree polynomial, we should have at least 6 coefficients. Since here we have only 4 coefficients, we need to find out the 5th degree polynomial, and that is the final highest degree polynomial that is to be accomplished with respect to the motions, right? So these are the differences which we have gone through. So in today's session, we have discussed about how to find out the highest degree polynomial with one sample example, and we have seen how to calculate the trajectory planning with respect to the acceleration and deceleration. Right, and in the first problem we have seen how to find out the time with respect to the different joints at a given time constraint. So we have calculated the time at different joints, right? So this is all for today. In the next class we will be discussing few more examples. Right? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.